There we go. Now it should be fixed. Hello and welcome. Today is Friday, May 15th. And this is the last of our lecture series on electromagnetic induction, which also happens to be the last of our lectures altogether. So this is it, the end of honors physics, I suppose, in terms of new content. Now you still have your Seneca learning assignments. I've been looking, I've been logging on and looking at who's doing what. More of you have started it, which is good, but some of the people that I've named last time who are on my bad list are still on my bad list. So please get that started. The science department has decided to move away from traditional testing for this semester, so please check the announcements on Canvas. These Seneca learning assignments are now basically your final exam, as that's the only thing that will come into the test category. The only other thing that's left is the Unit 10 Lab 3 and the Seneca Learning Assignment Final. So other than that, there is no other thing that will go into your grade. Alright, so let's finish off our year with our last lecture. All right. So last time we looked at all of the various magnetic forces that can be applied on various things. Here, let's pull up the summary here. Recall that we had F Bill. Bill is the force on wires. So anytime a wire carries current and that wire is in a magnetic field, an external magnetic field, it will feel a force. It'll actually move. And then similarly, we can actually go down to the particles. Any particle that is moving through space, that is, or I should say, any particle that's moving through space in an external magnetic field also experiences a force, and that's QVB. All right, and so we know that forces can, magnetic force can be applied to current. Or and anytime, I should go back. I skipped one. And anytime we have current flowing through in a wire, that wire creates a magnetic field around it. And if you were to loop it, we saw that the loop actually makes it look like a bar magnet, really. So this is how electromagnets really work at junkyards, where it's really hard to find big giant magnets by digging it up from the ground. So it's a lot easier to create strong magnets through electricity. So based on various formulas, of course, the more current we have, the stronger the magnetic field will be, etc. So for junkyards where you want to pick up giant metal cars and stuff, chunks of metal, the cranes will have like an electromagnet attached to it, and it'll just pick things up. So we know for a fact that electricity can produce the magnetic fields. And so back in the day, there was this scientist. This is actually one of my favorite scientists, Michael Faraday. He tried to experiment with various ways to use to use magnetism to produce electricity. So he's trying to go the other way, backwards. Right? We know that if you have current, there's magnetic fields around it, but can you use that to actually produce current? So in this setup, his idea is that, well, let me have this iron ring. Now the iron ring, obviously iron is conductive, but the wire itself is technically not the wire that you saw in a circuit diagram. This is real wire. Real wires are actually insulated. So therefore, when this real wire is touching the iron ring, there is no actual connection, meaning if there were charges flowing through the wire here, it's not going to magically move over to the other side, because there's really no connection. The wires are insulated. Okay, so the charges stay inside the wire. So what is he doing here? Well, he's using the battery to push the current. So the current comes out of the plus end, and then it loops around a couple of times, and then goes back into the negative end. But we know from last time, the last lecture, is that when you do this by looping it around, you're actually kind of multiplying the magnetic field that is produced by the wire. And so you're creating this. This here is actually an electromagnet. It's a solenoid. Solenoid is just the looped wire, but now that we have iron inside the solenoid, it's an electromagnet. So by doing this, we're producing a magnet. So his idea is that perhaps the magnetic fields, even though the charges can't move directly, perhaps the magnetic fields can push the current on this side, and then and then it'll be read by this thing called a galvanometer. A galvanometer is like a it's like an old-fashioned ammeter, if you will. It'll show you the push of the current one way or the other, if it's going in the positive direction or the negative direction. All right. And so his idea was that, okay, well, if I can produce magnetic field here on the left side, the magnetic field, which is not restricted by insulation. Remember, insulation only works for charges, right? Rubber and plastic and all these things are insulating the charges from moving from one wire to the other. But magnetic field can, go through walls even, right? So his idea was that, hey, perhaps maybe the magnetic field from this wire can push the charges on this wire and then produce current. And it was a brilliant experiment, but it failed. It didn't work. All right, the end. So he kept trying it over and over and over, and I think Einstein called it madness, where you do the same thing over and over, expecting different results. But it was noted that there was a small time frame, a small observation that he made, where in the moment he's turning it on and turning it off, there's a little blip on the galvanometer, meaning the galvanometer is reading current, a very tiny amount of push or pull of current, the instantaneous moment he's turning it on and turning it off. But if you just leave it on or you just leave it off, it doesn't work. Okay, so from there, he started to conclude things. He found no evidence when the current was steady, but did see a current when the switch was turned on or off. So he tried to do various experiments. Perhaps changing the magnetic field is the key. And so with that logic, here we have just a single looped wire. And so if you stick a magnet inwards into the wire or take the magnet outwards, it actually produces current. You can actually see that the fact that you're changing the magnetic field going through our loops has a magnetic force onto the charges that are inside the wire. Even though the wires are insulated, doesn't matter. The magnetic field will penetrate the insulation and it will push the charges in there. And so when charges move, moving charges is what we call current. Okay. And also notice the relationship. If you do the opposite, like here we're sticking the magnet in and we're getting positive current. If you take the magnet out, you get negative current, meaning the current is going in the opposite direction. And if you keep it steady and don't change anything, then there's no current. You get zero current. So there has to be a change. From there, we get into this idea of inducing voltage. Remember, whenever we have a voltage difference, that's when current moves. Current moves from high potential to low potential. Okay, the fact that the current is moving right now, even though there is no battery or anything, means that there's some sort of voltage difference between 2 points. Well, that's what the magnetic force is basically doing onto the charges that exist inside the wire. Right. And here we have our first law. The law tells you, this Lenz's law tells you how to actually find the direction of that current. The current will always go in a direction to produce a magnetic field of its own to fight the changing magnetic field from the external magnetic field source. Excuse me. This is quite complex, so this is definitely in the AP physics realm here, but we're kind of going above and beyond our class at this point. So what is the idea? So recall that anytime you have current, the current will produce a magnetic field. Okay, so we have a piece of wire or a looped wire. We're sticking a magnet in it, so kind of like this picture I just showed you, right? So imagine you being the wire. You have all of this magnetic field lines coming at you. Okay, It's almost like Newton's third law in that for every action there's an opposite equal reaction. So what does the wire do? As if it's alive, the wire produces its own magnetic field such that it will fight. When I say fight, imagine, when you have two magnets, the north and north will repel each other. So if you have a north pole coming into your looped wire, the wire itself will produce a magnet that has a north pole so that it can repel the magnet that is coming in. Okay, now it is a futile process in that you can definitely overpower that magnetic field. It's not going to be stronger than you, but it does tell us the direction of the current. The current will be in such a way that there will be a magnetic pull to oppose the change of the external magnetic field. All right, so I'm going to skip this. This is just showing you what the induced voltage is all about. Actually, let's not skip it. Imagine pulling a wire in a magnetic field. We know that using our right-hand rule, we can figure out the force on the charges. So if the charges are moving in a direction, we can say that the current is going in that direction. And based on the direction of the current, we can figure out the voltage difference. So which one's the high potential and which one's the low potential, because current always flows from high to low. And so based on that, we can quantify the voltage, the voltage difference. Remember, there's no battery here. This voltage is basically coming out from the fact that we are changing the magnetic field experienced by the wire. Okay, and how you experience can be in a multitude of ways, and we'll show that in the next slide. But basically, BLV shows you the amount of voltage in a piece of wire based on the magnetic field B, L being the length of the wire, and V being how quickly the velocity, how quickly the wire is moving. So whether you move the magnetic field or you move the wire, you're going to produce some sort of voltage here. So what are other ways to produce voltage? Faraday did many experiments. Okay, so moving the loop into or out of the field. Okay, anytime you move the loop of wire in or out. Okay, and then rotating the field. Rotating the making the loop rotate in the field. So when you rotate the field, okay, the field you want to imagine as vectors, they're arrows. The fields cannot go through the hoop. So if your hoop is like 90 degrees to the field, then the arrows can't really penetrate the loop. Therefore, it doesn't actually produce voltage. Making the field stronger or weaker, so changing the strength of the field, and of course changing the area. So all of these changes can produce some sort of a voltage difference, which forces the current to move inside the wire, even without a battery or a power source. So and so we give it a term. We call it magnetic flux. Flux is the amount of the magnetic field that goes through any given amount of area. Okay. And to measure it, we just take the area A times the field strength B. Now, it is a dot product, so those of you who are in calculus, you'll know definitely what this is. But basically, it's the magnitude of the dot product gives you AB cosine theta. It's just like the work equation. Recall that work was equal to F dot D, or force times distance times cosine of theta. Basically, what we're doing is we're finding the x component, or the parallel component of the magnetic field to the area. Now, area as a vector, area is 90 degrees to the surface. So if you have an area like this rectangle here, the area vector would be 90 degrees to the surface. And so 90 degrees being, in this case, with a vertically oriented area, our area vector would be horizontal. And what we're doing is finding the component that is parallel to the area vector and then just multiplying. So AB cosine theta. Theta being the angle from the horizontal from 3 o'clock going to the up to whatever the magnetic field is. It's the angle between area and B. Magnetic flux is measured in Weber's WB. These are just JFF, just for fun. And so based on this flux, we can figure out what our voltage is. Voltage is the change in flux for change in time. If you're in calculus, you know this as the derivative. So the derivative of flux as a function of time is the voltage. And if you have more than one loop, it linearly scales. So 2 loops is twice the voltage. You just multiply it by how many loops you have. So what are all these things? N is the number of loops. So in your coil, how many loops you have. Delta phi means the change in your flux. Now if we go back, the flux is area times magnetic field times the angle. So any 3 of these variables can change. We just do final minus initial. Remember, delta is final minus initial. Excuse me. And so here's an example of this. So we have this U-shaped wire and this bar, metal bar, that you can kind of pull to the right. That's what it's showing you. Notice that by pulling this bar to the right, the area of the loop, here's the loop. The loop consists of this U-shaped thing and this bar. Okay, as you move the bar to the right, the area is actually increasing. When the area increases, the flux increases. Flux meaning how much of the magnetic field goes through the area, AB cosine theta. So the flux increases. Notice how we have this external magnetic field. The external magnetic field is pointed outwards, which means that it's coming out of the screen here. When I change the area, there are more magnetic field lines going through the area here. And so what the wire does, what this coil does, is that it will produce a magnetic field of its own to fight this change. So if I have more magnetic fields coming out, the wire is going to produce a magnetic field that goes in to cancel out some of the excess. And so through that logic, the wire will push the charges in this clockwise fashion, and by doing that, so by pushing the charges in this clockwise fashion, the current will then produce a magnetic field that goes into the board, and it will somewhat cancel out the excess, the new amount of magnetic field lines that are going through the area. It's almost like trying to stay in status quo. If you're in AP Chem, you know all about buffer solutions, right? You're trying to stay in equilibrium. If you go one way or the other, the system will try to equilibrate, going back to status quo. So if you shrink the area, then the current will reverse direction and go the other way in a counterclockwise fashion to produce more magnetic field coming out of the board, because you're now losing instead of gaining. So the direction of the current will change based on what is happening to the amount of magnetic field that is going through the area, through the window. All right, what is all this for, really? All of this talk. Well, what can we do with this? Well, we can produce electricity. This is how we get electricity in our homes. Electromagnetic induction. There are many ways. In essence, somewhere far away from our homes, we have turbines. Turbines are generators, or turbine generators, are basically things that are spinning. You can produce it by spinning a magnet in a coil, or traditionally you can have the magnet in place and have the coil move around. So either way, you can actually generate electricity that way. First of all, you do need mechanical work to spin. Now, you can get the mechanical work if you think about water wheels. When the water falls onto this wheel, the water pushes onto the wheel spins and rotates. We are converting, gravitational potential energy, pegmega of the water, crashing into the wheel, turning into rotational kinetic energy for the wheel, right? And so hydroelectric dams do this, where the falling water pushes onto the turbines and forces the turbines to spin. So here's a simplified model of a turbine generator. In that when you rotate, here we have a rotating coil inside a U-shaped magnet. So the magnetic field is stabilized in that it's just going from the North Pole to the South Pole, so it points to the right. But as the wheel turns, the coil turns, and as the coil turns, there's a different amount of magnetic field that goes through the loop. And this changing magnetic flux, which we call the area times magnetic field times cosine of theta. So as the angle changes, as theta changes, there's a different amount of magnetic flux. Therefore, due to this change, we now induce a voltage which pushes the current, and this is what we get, right? Unfortunately, I can't show you the generator demo. What we get is a sinusoidal curve, and it goes back and forth. That's because half the time the magnetic field is going into the coil, from the face to the back, so to the right. Now, when the coil rotates all the way around 180 degrees, now it will seem like the magnetic field is going in the reverse direction, and because of this, the voltage is now the current is now going in the other way. So this is how you produce AC current. Okay, this is why you have alternating current. The alternating current actually gives you alternating voltage. Okay, and so it oscillates between a positive value and a negative value. So at any point when you're using alternating current from the outlets, okay, half the time the current is coming in through one prong. Remember, when you connect a plug, you know how there's like two little prongs, two little metal teeth. Okay, and half the time the current is going in through one, and then the other time it's going out through that one. We're gonna skip all that. Yes. In America, we're using somewhere around 110 to 120 volts. If you go to other countries, the voltage is different. That's why you need like an adapter. Our alternating current comes, at 120 to 110 volts, and it alternates. Remember how it goes back and forth? It alternates 60 hertz, meaning 60 times a second. It goes back and forth. Light bulbs are turning on and off 60 times a second. But it's so fast that it looks like it's always lit. In like Asian countries, the voltage is twice as much, to around 240 volts. In European countries, their frequencies could be at 50 hertz, like PAL. If you've ever imported video games, like old-fashioned video games from different countries, back in the day, before before you could just download everything in online gaming, you'd have to play games on CDs and stuff. It's kind of like your console gaming. And if you imported video games from other regions, then it wouldn't technically work because they're made for different frequencies. So you'd have to get like something called a mod chip, where you modified your console so that it could read those discs. All right. A motor is essentially the reverse of a generator. Okay, so what is a generator? Well, the generator converts your mechanical energy into electrical energy, right? So from peg-mega to KE, and then eventually from KE to electric potential energy, PEE. Okay, a motor is essentially like a generator, except it runs backwards. It uses electricity to force it to spin, so it converts electrical potential energy back into rotational kinetic energy and other things, right? Now, washing machines, hair dryers do two things. There's a fan and a resistor. So the current is used to heat up the resistor, and then at the same time it is also used to turn the fan on, and so the fan blows air through the hot resistor, which produces the hot air. Skip all that. Nikola oh look, Tesla, there he is. So a lot of the inventions of motors and other things, induction motors, was all made by Nikola Tesla. He doesn't get very much credit for a lot of things, um, and there are reasons for it. There's some political reasons for it. His competitor was Thomas Edison, and typically Edison was funded by the government. He had connections to the government, so he was funded. Same way how it really works these days. You have lobbyists that eventually get contracts for their companies, and then the companies make bank by producing things for the government. So similarly, Thomas Edison got all that funding and stuff, whereas Tesla kind of was on his own. So didn't get as much credit for a lot of things, and therefore he, because of lack of funding, he wasn't able to do so many other ideas that he had. For example, the wireless power transfer. It was a concept that he had. He wanted to transfer electrical energy through the ground so that everyone had free energy. Oh, I shouldn't say free. I mean, no one had to pay for. I should say no one had to pay for electricity. But instead, Edison went the other way, I guess, to make profits. But now we can take multiple assessments of what went on and how it happened, etc., without me giving my opinions. So I'll leave it at that. All right, and the last thing we can do with our concept is change the voltage. And so you might be wondering, how do I get an adapter so that I can use my electronics when I go vacation in Europe or something, right? Well, transformers are your friends. These are not Optimus Prime and those types of transformers, Autobots, Decepticons. You've probably seen them somewhere, like on a pole, somewhere up on a pole, like a wooden pole. You'll have these metallic trash cans. It's Optimus trash can. Inside is basically Faraday's experiment, and we'll show you that. When you're producing electricity at the power plant, it comes out at very high voltage. We actually up the voltage, so there are transformers that increase the voltage, and there are transformers that decrease voltage. Now, increasing voltage doesn't mean you somehow got extra energy or something. There's no such thing as free energy. You can have higher voltage, but at a cost. So less power, less current. But we want high voltage so that there's less loss when we're transferring from from one part of the state to the other. Remember, these things are produced far away from us, and then on the freeway you'll see these big giant electrical poles, with these high voltage wires. When it says high voltage, it's carrying super high voltage, like 240,000 volts across the freeway. If you're on your way to like Las Vegas on the I-15 or something, you might see all of this stuff. And then eventually it comes into somewhere around your neighborhood, and then there's probably a region somewhere in your neighborhood where it's all gated up. There's like metal fencing everywhere, and inside that facility are all these step down transformers. So it takes all this high 240,000 volt lines, and then steps it down, and then it sends it through regular electrical poles, the wooden ones that you have everywhere, and then those trash cans that I showed you, these gray things, they step it down even further from 240 in this case to 120. So the difference being in other countries is that they just don't take the time to lower it. So what are the cost and benefit? Well, remember, you're using more resources to lower it further, but at the cost of power. So you have higher voltage. It's technically a little bit more dangerous, but you can run more things. So that's kind of a decision the governments of various countries would make. For the most part, like the big giant plugs that you have for your electronics these days, the big giant plugs actually have transformers in them, meaning it already can accept anywhere from 110 to all the way to 240. So whether you're in America or In Asia, it doesn't really matter. You can actually plug it in. You might now, the plugs themselves are slightly different. You know, in other countries they have like rounded ones, so you may need an adapter plug that changes the shape of the plug. Let's see if I can pull something out. Images, plugs. Yeah, here we go. Here are some. Oops. Here's some plugs. These things. So in different countries, you have different types of plugs, like different shapes. Now these things don't actually change the voltage. Right. Oh look. So here's some various types. These things don't actually change the voltage. They just change the mechanical design of it, meaning you can put your plug into it and then it can connect to the outlet. Your box, the actual box, has to be able to change the voltage from 110 to 120 or whatever. So typically the newer adapter plugs even can accept anywhere from 110 to 240, and then it actually converts that AC power to DC. DC means direct current, which is a constant value. Most electronics just use DC. That's why the battery, when you have a phone, right? Your phone has a battery. The battery gives it DC, a constant voltage. Okay, but you're also able to charge your phone through your outlet, but your outlet is AC. So how does that work? Well, your adapter is actually converting not only the voltage but also converting the style from AC to DC. AC DC. And typically it lowers it to to various voltages. If you actually look inside of a plug, you'll see that each not a plug, I should say, a connector, like a USB-C connector or whatever you have, lightning connector. They have tiny little slits of metal slits. Each slit has like a different voltage value. One of them is like 0, one's negative, somewhere like 12 volts, 24 volts, whatever it is. And so the adapter is doing all of that and then sending the lower DC voltage into the electronic device. So what is a transformer? A transformer looks exactly like Faraday's experiment, except he doesn't have to have a switch that turns on and off now. But we had to turn it on and off to change the flux or change the magnetic field, right? But with AC, it is already alternating and it's already changing, and so you can just directly connect it without a switch. So due to that alternating, changing magnetic field, it actually produces electricity on the other end. So on one side of the iron ring, we have a certain amount of loops. On the other side of the iron ring, we have more loops in this case. And so the difference in the loops will essentially give us a difference in the output of our voltage. And it's a very simple relationship. It's like a ratio. So this is primary, secondary, if you want to think about it, input, output. Primary is input, secondary is output. So the voltage in the primary, the input, divided by the voltage in the output, Vs, the secondary, is equal to, in ratio of, just the loops. So voltage primary over voltage secondary is equal to loops, the number of loops, I should say. N is the number of loops. N is the number of loops. N is the number of loops. So the loops in the primary coil divided by the loops in the secondary coil. And so if I have here, if a primary coil has 75 turns, how many turns are needed so that the transformer can convert 120 volts to 2400 volts? Okay, so we can just set up our ratio. So we say the primary loops is 75, the primary voltage is 120, the secondary loops, I don't know, that's what we're trying to find. Secondary voltage is 2400. We set up this ratio, cross multiply, and then solve. So our secondary number of loops is 1500. So if I have 75, so if I have 75 turns here, and then 1500 turns on this side, then by sending 120 volt AC volt or alternating voltage through, we'll get alternating voltage at the other end, but it's at 2400 volts. Okay. Now we didn't produce free energy. There is a loss, the energy actually has to be conserved, right? Usually you're always losing a little bit, so the power rating is actually down or something like that. All right, so that's the end of the slide, which means it is the end of our lecture series. Whoa, we did it. This is it, the end. So where do we go from here? Well, you want to think about all the various topics we've learned and how everything kind of works together in our world, really. The future is to produce various things, from designing physics engines. So the hottest and the newest, latest tech is to design newest physics engines where you can simulate physics in the virtual world, right? Imagine doing all those testing. Anytime you have a product, like say you want to design a car, a new car, you have to spend millions and millions of dollars crash testing and trying to figure out safety concerns and figure out where the break points are, so you can reinforce certain sides and all that stuff. If you can produce a physics engine that can simulate a lot of those testing things, you can reduce the amount of resources required in the real world, and by just simulating everything in the virtual world. So there's a big push in designing physics engines and doing virtual testing. But eventually, yes, you do have to do real world testing, but it's just offloading some of the workload. Recently, Unreal Engine 5 just came out. I used to joke about Unreal Engine 5. It's like, oh, use your Unreal Engine 5 in your brain, and now it's an actual thing. And you can take a look at a video like Unreal Engine 5. And of course, the last bit, the next frontier is, of course, in artificial intelligence and AI, and developing circuitry and basically circuitry that can learn. This neural network stuff that they're talking about. You are using patterns and other things to from experiences, just like people, really, and then you use that to reevaluate how to solve problems and come up with new solutions. So it's like iterative learning. The future is very interesting. For some it could be scary, but those who are ready, those who are well in tune, those who have studied physics, can definitely take advantage of all of their knowledge and be at the forefront instead of the back end. All right, well, I'm gonna stop babbling. Thanks for tuning in. This is again the last of our lecture series. Your only assignment is to finish up your Seneca learning assignments, which is your final. You can always email me if there's if anything comes up, but I can't technically help you on the assignment itself because it is your final. but other stuff, like perhaps something's wrong with your grade or something, definitely email me and I'll be around to answer those types of questions. All right, well, thanks for tuning in. I'll see you when I see you. For seniors, best of luck if I never see you again. It's unfortunate that we couldn't do a lot of the stuff, all of the projects and all that stuff. I wish you all the best. Juniors, you can always take AP Physics next year. But see you later.